Welcome to another teardown. This is a monitor. It's standalone. It has a paper printer in the back, blue tack on the sides with some wires hanging up, because this is a pre-production demo version that I've had for a while, and you can tell that it's made for the medical, because all the connections are quite hard to actually get into. You know, when the power supply was plugged in, you wouldn't be able to touch any metal there. When the various pieces of kit are plugged in, you can't easily get to anything. And like the main screws at the back are plastic or nylon. All the other screws are well hidden, because obviously this needs to be safe for the patient. So let's have a look at what's inside. Well, this one was going to be just a 10-minute teardown of the medical monitor, but I thought the isolation requirements for the patient was of more interest than just pointing out what components are fitted to the board and how big the memory is and how fast the micro is. So I've changed track. So, you know, the teardown is now only going to take half a minute, and then I will talk a bit more in detail about the isolation between the two important parts of the PCB. So let's have a closer look at the board. There are, as you can see, two main sections. There is this side where the 12 volts AC power comes in, which of course is transformer coupled to the mains by a step down transformer, and earthed to the mains as well. Now this side is the patient area. Now there are three sort of types of connection to a patient. There's type B, which is where it's like non-conducting and it doesn't stay on the patient for a long time, which could be something like you know, if you're having your eyes tested and you rest your head against a piece of foam, on the unit, then that foam will be a type B, because it's non-conducting and it's in contact with the patient, and so you have to follow the rules on what the foam can be. Now if there's electrical side to it and it touches the patient, then it becomes a type BF, which is body floating, which means, you know, there could be an electrical connection to the body, there's metal parts, but they're only touching on your skin, so the skin's got quite a high resistance, so it's you know, it's not life threatening, but it's more stringent, that you have to put more precautions into leakage and things like that. And then there's the final one, which is type CF, which is cardiac floating, which this board is made for type CF, because the sensor that plugged into there actually connected to the patient's arterial line, and so any power present on here was actually present on the patient's arterial blood, and the actual sensor did actually put a voltage across a voltage onto the blood to set it to a reference level for the sensors that are in there. And so that's why this section has got such a good isolation, as you can see here. You know, silk screen. Don't know if you can see that. Just trying to get it. It's a good 8mm of track missing. So between the ground plane on here and the ground plane on there at Nini Signals, there's a good 8mm. And of course the important ones are the creepage and clearance distances. Well, on this part here, creepage from here across the board to there is the same as the clearance from that point to that point. But you'll notice under these chips, sorry for that, under these chips you'll see there's a slot cut. Now that effectively opens up the creepage. The clearance is the same because it's from this point to that point, and it's not going to get any work, it's not going to go away because that's the size of the component. But the creepage, which is where if there's moisture on the board and things like that where current can track, of course it now gets to that slot and can't go any further, so it has to go around it. So for things in the middle, the creepage is considerably increased because it has to go around that slot. And sorry, it's sticking in my throat. If you turn it over and look on the other side, you can see the isolation is still maintained, the clearance is still maintained at 8mm, and then you can see the slot for those components. Now we'll have a look at the data sheets in a minute, because I can't find a data sheet on power supply, but I know it's a 5V DC converter, and it's a medical grade high reliability converter, and so the isolation on that will be as good or better than what's on these chips. And we'll look at the data sheets that these are digital bridges, so digital signals from here can migrate to here, and there are 3 going in one direction and 1 coming back. And as you can see, they are rotated round. So in one of these there'll be 3 data signals coming this way and 1 data signal coming back, and on the other one there'll be 3 going this way and 1 coming back. So it's got, like, 4 channels this way, 4 channels that way, and a spark gap, so that if anything, like a nurse or someone comes up and she's charged up with some static by accident, she'll touch the connector, or as the connector goes in, any high voltage static will discharge through this and be removed before it's connected to the patient. So I'll try and get call up the data sheets now on these, and we'll have a quick look. But you can see, unlike on these cheap power supply boards that you see where there's a millimetre of clearance, this has got considerable clearance gaps and slots and high reliability components. So as we can see here, this is the data sheet for the quad channel digital isolator. So there's 2 of them on the board, and it's the ADUM2401, which is this baby here. And as we can see from here, there is 3 channels going from the low side pins to the high side pins, and 1 channel coming back from the high side pins to the low side pins. So with 2 of those chips, it's giving us 4 channels in each direction. And the important bit down here, you can see that transient immunity 25 kilovolts per microsecond, so it's pretty good at that. And then this is the important area down here where we look at the safety and regulatory approvals. You can see that it has approvals for IEC 60601-1, which is the electrical safety standard for medical equipment. And so it's been designed with medical applications in mind, and you can see it is a transformer, so it's high speed. You can get good, you can see you can get 90 megabits a second for it. I don't think in this application it runs anywhere near that fast, as I think it's only sort of RS485 going through and some other control signals. Not sure why for the 60950, which is the sort of PC IT standard, well, it's rated higher, but there may be a different test involved for that. But as you can see, you know, it's designed for that use. And you know, we might go down here somewhere, any leakages, if it's got any leakages across it, supply currents, thresholds, pulse widths. I know I should have looked earlier, but is there anything? Because you know, with no, I'm not going to carry on looking down there anymore. It's all just different speeds and switching. Oh, we're into packages now. So when it comes to cardiac floating, you know, you have very low leakage currents that you're allowed. You know, 10 milliamps is the maximum leakage to earth that you're allowed. And you know, when you start looking at bits more of the standard, you get down into microamps of allowable leakage. And of course, this system also had to survive that while it was connected to the patient, you know, someone might come along and defib the patient, and they will not go, oh, before we defib him, let's remove anything plugged in. You know, it's get out the way, paddles on, bang. And so this equipment has to be designed so that when it sees a defib pulse, it curls its toes up, waits for a few microseconds, straightens them out, gets back on doing its job. You know, if it dies, then it's no good to anybody. So, you know, we did a lot of testing with defib units and electrosurgery knives, which of course are RF, to make sure that while all that's going on in the patient, the sensors are not dying and can carry on functioning normally once the interference has been removed. So I think that's just a quick insight as to what you need to do if you have a patient attached to something. I think it's getting a bit long, this waffle on this one. So we'll go and have a look at another data sheet. Right, just a quickie. This is the other component bridging the gap, apart from the power supply. I can't find any details on the power supply, so we'll just have to leave that one alone. As you can see from here, it's a linear octocoupler, whereas a normal standard octocoupler is just digital. You know, light comes on, transistor turns off or turns on, inverts or it doesn't invert, and you know, it's just that's what it does. Whereas you can see here, this is a linear octocoupler. So we have two LED, or an LED driving and two sensors, so that you've got a control loop and an output. So rather than just feeding a signal into it and not knowing what's coming out, you can see the signal in, monitor the signal in on this side, so that you know the signal coming out that side is exactly the signal you want. So you've got, on your input side, you've got a feedback loop which allows you to correct for temperature drifts and everything else, and gives you a nice linear flow across. You know, if you didn't have that feedback, then you wouldn't quite exactly know how much light's coming out of that one and how much current is being, you know, converted on this side, and so you wouldn't know if your signal is coming across properly. At least this, you have a feedback and you have a reasonable idea of what, you know, reasonable control of what's going on. And as you can see, you know, it's got UL approvals. They say it's medical sensor isolation. Its isolation is rated to 4,420 volts RMS, so reasonably high. And it's probably, as you can see, they do different widths, and as you can see that our board was 8mm ish, so it's probably that body size with the legs coming out to about 8mm. You can go wide. There's a wider body one which will probably give the best, that's going to give you the best clearance size. And all the clearances and creepages are all specified in the medical standards as to what you can and what you can't do. And part of getting all this certified is the cost of having someone come down and rip this apart and measure all the gaps, measure all the creepages, clearances, looking at the chips. If there's a chip they're not quite sure about, say the power supply, they can't find all the correct details, then they will rip that power supply apart very carefully and measure it. Even when you have a transformer, mains transformer that's rated to medical, if they don't trust the paperwork, they will physically rip your transformer to pieces, taking detailed measurements of wrappings of cables, covering insulation, material types, flammability. They'll do everything to it, and if they're happy, they then sign it off. So this can cost many thousands and thousands of pounds to get something like this through certification. This one didn't go through full certification, say, because it was just a demo. And I'm just waffling now and moving this up and down. As you can see, like isolation resistance greater than 10 to the 12 ohms. So greater than 7mm creepage, greater than 7mm clearance. So it's all adding up. You can look for all the common factors that are required for a medical piece of kit. Right, I think now that's a bit much that's a bit more waffling than I intended to do. Is it was just going to be a break from this is the components and this is what they look like. So if you still want to subscribe, hit the subscribe button down here. If you like it, if you like it, hit the like button, and of course the notification bell if you want to be notified. And I think there should be a little TEH in the corner now. Click on that and it should let you subscribe. Okay, I'll catch you next time. Bye for now.